Hey there, stats enthusiasts. Welcome back to our series on the chi-square distribution in AP Statistics. In this section of notes, we are going to be going over notes 2 of Unit 8. And in this section of notes, we are going to be covering the chi-square test for homogeneity. Now, this test is going to introduce a two-way table, a contingency table, and talk about how we check to see if what we observe in that two-way table is what's expected. So go ahead, grab your notes, get settled in, and let's start learning together. The test we are going to learn about today, the chi-square test for homogeneity, is actually going to expand on the idea of a two-proportion z-test. And I say expand on the idea because the type of question we could answer with a two-proportion z-test can actually also be answered with a chi-square test for homogeneity. But a chi-square test for homogeneity is going to allow for more populations and more categories of our variable than the two-proportion did. So we know the two-proportion z-test, it compared the proportion of successes just between two populations. And each population had a single proportion. And then we compared them to see if there was a significant difference between those two populations. Well, our test today, the homogeneity test, will allow us to compare the proportion of successes across several populations. And the proportion of successes will also have its own number of categories as well. So here's the example we're going to work with today. After turning the age of 18, do males and females differ in their living arrangements with their parents? So we select two separate random samples of 200 males and 150 females who are between the ages of 18 and 20 and ask them where they live. And here are the results. So this idea that it's two separate random samples, that is going to be important for our test. Okay, so it's stratified in some way. And we have two separate male sample and a female sample. Now, we can see here how our two populations, we just have two populations right now, male and female, but you can see how with a two-way table, we call this a two-way table because information's going two ways here, we can see how we can have as many populations as we want. So male and female, just two populations, but maybe if we had, grade levels, so like freshman, sophomore, junior, senior, that would be four separate populations. So however many populations in your problem. And then we look at, in this situation, where they live. So we look at how many males and females live in each of these categories. Now, a two-proportion z-test might have had us only looking at, let's say, with the proportion of males and females living with their parents, right? So do the proportions of males and females differ when they live with their parents after the age of 18? Might have been the type of question to ask for a two-proportion z-test. Now we're going to look at it across all of these categories and see if there's a difference in male and female living arrangements. So the way we set up these hypotheses to answer the question. So here's kind of the template for the null hypothesis, is that there is no difference in the distribution of a categorical variable for several population or treatments. And of course, that's the generic version of it. We always want to put these hypotheses in context. Okay. So with the chi-square test, we're starting to write the hypotheses just in words. With the goodness of fit test, I said you could write it in words or with symbols. And with the homogeneity test, it is much easier just to write it in words. So in our example, we would say there is no difference in the distribution of living arrangements among males and females. So our null hypothesis is still always that statement of no difference, okay? Just like it was with the two-proportion z-test. There is no difference, right? We assume that it's not necessarily an even distribution because that would imply like even expected counts, but we expect that there's just no difference in the distribution of those living arrangements. And then the alternative is the opposite. Without context, we would just say that there is a difference in that distribution of that categorical variable. So in our context, we would say that there is a difference in the distribution of living arrangements among males and females. Okay? So remember what this is not saying. This is not saying that all of the proportions are different, okay? Just that we detect a difference. We ran the chi-squared test for homogeneity, and hey, we detect a difference. That difference might be isolated to just one or two proportions. That difference is not necessarily every proportion in the distribution. And that's an important distinction to make, because in the goodness of fit test, we also said that our null was that there's no difference in the claimed distribution, but our alternative was at least one of the proportions was different. And it's the same thing here. It's just saying that there's no difference in our claim. Our claim is that there's no difference. That's our null hypotheses. And our alternative is that, hey, we detected a difference. Not necessarily that everything is different, but we just detected a single difference, okay? Now the expected counts. So we are still going to be comparing what we expect the count to be with what we observe the count to be if the null was true. So to find the expected counts here, we are going to start by assuming that the null is true. And in our example, that would mean assuming that there's no difference between males and females in their living arrangements. Now, we expect this proportion of males and females to be the same across the living situation, but not the expected counts to be the same. Okay? The proportion's the same across, but not the counts. And that's very important. Okay, so to find the expected counts, we use this formula, okay, this following formula. And this formula evenly distributes that proportion across all categories. Now, the counts will not be the same. The expected counts will not look the same because males and females had a different total sample size. Females had 150 in our example, and males had 200. So the counts are not going to look even, but this formula is going to give us that even proportion across all of the categories. So for each count in each cell, you're going to take the cell's row total and the cell's column total, multiply it together, and then divide by the table total. So here's what that is going to look like. So off to the left, I have the observed count. So this was what was given in the original problem. This is what I observed. So when I want to find the expected counts for each of the 6 cells, and remember, we don't find expected counts for the totals. We just find expected counts for the cells. I look at if I want to find the expected count for females who live with their parents. Okay, so females who live with parents, I observed 61 of them. I'm going to look at the row total and the column total. So the row total for female is 150, and the column total for living with parents is 121. So I'm going to take those two values and multiply them together, and then divide by my table total of 350. And that's how I find the expected count in that single cell. So when I do that, I'm going to get the value of 51.86. I like rounding to just 2 decimal places. You can also round to 3 decimal places here. You don't have to go crazy with the rounding. But you're going to have 51.86 as your expected counts of a female who lives with their parents. And you're going to do this for each cell. So if I want to know female who lives in their apartment, I observed 29. So to find the expected count, I take the row total of 150 and multiply it by the column total of 56. And then divide that by my table total of 350. I do that and I get the expected count of 24. And I'm going to continue doing that. So female in dormitory, the row total is 150, the column total is 173. So I'm going to multiply 150 times 173, divide by the table total to get 74.14. Now, if you add up all of these expected counts, you do get 150, okay? Because that is all of the females distributed in proportion across the 3 categories, okay? And the proportion they're distributed is based on the total, okay? The total of the columns. So we're going to do the same thing with males. So for males with parents right here, the row total was 200 and the column total was 121. So we multiply those, divide by 350 to get 69.14. Okay. You'll also notice if you add up the 2 expected counts in the column, you will get 121. You'll get that column total as well. But you continue doing that until all of your expected counts are full. Now, in the 4-step process, the communicate, conditions, calculate, conclude, you do not necessarily have to show this work right here. Okay. You can just make a table and write down the expected counts, but it's not wrong to show the work as always, but you don't have to show that work. Okay. For us, for this example in the notes and then in the homework as well, we are going to be finding these expected counts by hand because you have to know how to find them by hand. But you can see how with some larger problems, how this gets a little tedious and can take a long time. So in the next set of notes, notes 3, I will be showing you how to use your calculator to find these expected counts a little bit easier. Your conditions now, okay? For your conditions, they're going to be the same 3 conditions that we had for a goodness of fit test. Random, the data should be collected using a stratified random sample or a randomized experiment. Now, I specifically say stratified in this situation because in a chi-square test for homogeneity, you do have to take separate samples from your population. So yes, we're still taking a random sample, but it's just going to be a stratified random sample. You can also have a randomized experiment where each of your populations represents a different treatment, and you randomly assign to each of those treatments. That is another way to meet the random condition. If you are sampling without replacement, so if you are taking a stratified random sample, you do have to check the 10% condition for the table total. Okay, so 10% condition for the population as a whole. So even though we have separate males and females groups, you don't have to check the 10% condition for each group because it's a stratified random sample. So your entire population is student, in our example, let's say, is students after they turn 18, between 18 and 20, I think were the ages, we want to check the 10% condition on the entire population. We stratified it into males and females and took separate random samples, but our entire population was students or adults who are between the ages of 18 and 20. Okay, so you check the 10% condition just for the table total of your entire population. And then the large counts is the same as our goodness of fit test. All the expected counts across every cell must be greater than 5 or equal to 5. They can be equal to 5, but greater than or equal to 5. And then what do? Well, we calculate our chi-squared statistic and our p-value. And the nice thing about the homogeneity test is the chi-squared statistic and p-value is calculated the same way as our goodness of fit test. So we still have our familiar chi-squared statistic. This time, though, the degrees of freedom, because we have 2 categories now, or 2 variables, are going to be just calculated a little differently. Now it's going to be the number of rows minus 1 times the number of columns minus 1. Okay. So number of rows, that's how many are going to be in our example, it was males and females. So it's how many populations we have or how many different groups in our populations we had. And then the number of columns represents the number of categories across the variable, what are your living arrangements. Once we know the chi-squared statistic and the degrees of freedom, we can find our p-value. And that's using the chi-squared CDF on your calculator, the same as always. We're looking to see what's the probability that we get this chi-squared statistic or more extreme, so off to the right. So that's why your chi-squared statistic is going to be your lower boundary and your upper boundary is always going to be positive infinity. All right. Now let's answer this question, right? We kind of did a lot of these pieces together already. Let's do the full 4-step process here. So do males and females differ in their living arrangements with their parents? Okay, so here's the observed counts again. We've seen these. The question, do the data suggest at the 5% significance level that males and females differ in their living arrangements? So our null and alternative we've already done. So let's write it down here in the space. The null is that there's no difference in the distribution of living arrangements among males and females. And our alternative is that there is a difference in the distribution of living arrangements among males and females. So we always want to put context to those hypotheses, but it is going to be just a subtle change of there is no difference and there is a difference. And our expected counts, I put them here, but we've already found them. Okay, I put the work as well just to remind you of the row total times the column total divided by the table total. But if you just make a table, label the table, make sure that you fill in, like the female, male. I always just copy down the same table that they give in the problem. And I leave out the totals because I don't care about the totals when it comes to my expected counts. So I copy down that same table and then I fill in with these expected counts. Okay. So all of those expected counts get filled in the table. Okay. And right now we do it by hand. So just bear with me on that until we learn how to use our calculator for a little bit easier of a time. Conditions next. So two separate random samples were taken, right? We had a random sample of females and a random sample of males. Independent is the table total is less than 10% of all people between the ages of 18 and 20. And then large counts, we just calculated our expected counts and we saw that all of them are larger than 5. Okay. As I said before, you do have to write down what your expected counts are. You can't just state this and then use your calculator to find the chi-squared statistic. You do have to show those expected counts. That's part of showing your work. So make sure you make a table and show those expected counts. As far as our chi-squared statistic goes, we do it for each cell. Each cell we compare the observed count with what we expected. So for females living with parents, we'll start in that cell. We observed 61 females living with their parents, and we expected 51.86. So this whole piece, this is called the contribution of females who live with their parents. And then I move on to the next cell, and that's going to be females living in an apartment. I observed 29 females living in the apartment. I expected 24. So I do that contribution. Now, when you're actually writing this out, you don't have to write out all 6 contributions. For the AP exam, they are happy if you show the first 2 contributions. If you put a little plus ... to show that pattern is going to repeat. And then if you put the last contribution here, right? Just to show that the pattern is going to repeat in the same way that you are putting it down in your paper. So this last one was males living in the dormitory. We observed 113 males living in the dormitory, and we expected 98.86 living in the dorm. So we write down that last contribution. Now feel free to write out all 6. I'm not stopping you there, but you don't have to write it all out. You can show just some of the values plugged in. Make a little note here. This is how we say in math speak that the pattern is going to continue on, and then write that last piece there. We'll use our calculator. I know it's 6 contributions, so it's a little bit of alphabets, or and I guess not alphabet soup, number soup in your calculator. But be smart with your calculator. Keep it organized, and you can see that the chi-squared statistic is going to be 9.365. Once you have that, you also need to calculate your degrees of freedom before you find your p-value. Now I had 2 rows. I had males and females, and I had 3 columns, the with parents, in apartment, and dormitory. So 2 minus 1 is 1, 3 minus 1 is 2, and then 1 times 2 is going to be 2. And that's how we get degrees of freedom are going to be 2 here. Okay. And then from there, we get our p-value. So on the calculator, that was your chi-squared CDF. Your lower boundary is 9.365. Your upper boundary is positive infinity. And your degrees of freedom are going to be 2. Okay. Don't write this down. Don't write down calculator speak on the AP exam. Okay. If you write this down and the degrees of freedom down, and then you write down your p-value, that is totally fine. Okay. That is fine. You are good to go there. All right. One thing you also have to do here that I also left out is you do have to name the test. I don't think I named it on the last page, but you do have to name the test. And you can't just call it a chi-squared test because there's 3 different kinds of chi-squared test. You do have to name it a chi-squared test for homogeneity. Okay. at some point, whether it's the first thing you do on your page, whether you just write it off to the side, you do have to name your test. Okay. With other inference procedures, I always said that you could name the test either by words or with the formula. And for this, because all three tests use the same chi-squared statistic, you do have to be very explicit and name it by the actual name of the test. Okay, so at some point, write down this is the chi-squared test for homogeneity. Okay. And then once we have our p-value, we can wrap up and do our conclusion. So because our p-value of 0.00926 is less than our significance level, we will reject the null hypotheses. We have convincing evidence that there is a difference in the distribution of living arrangements after high school among males and females. Okay. So when we reject the null, we have convincing evidence of our alternative. And thankfully, our alternative was already written out in context. So we just write down that alternative in context when we are done. And that is your chi-square test for homogeneity. And that wraps up our lesson today on Notes 2, the chi-square test for homogeneity. In the next section of notes, we are going to be working on our calculator commands for the TI-84 and how we can use those calculator commands to help us with these chi-square tests we've learned about. And then we are also going to be talking about a follow-up analysis and how we can use that to our advantage when helping us draw conclusions about these chi-square tests. As always, if you have liked this video, please go ahead and click the like button and subscribe to my YouTube channel for more great AP statistics content. Until then, I wish you endless statistical success, and I will see you in the next video.